Thanks for coming again. Haven't lost too many people today, I think. Okay, so this is the second and final part of the introduction to pattern recognition. Yesterday we stopped at this point where I wanted to say a few comments briefly about, particularly in the context of faces, the differences between detection and verification and recognition, which are not always appreciated. So face detection, or pattern detection in general, is about finding patterns of some class in the data. So in the case of face detection, is the input pattern, the input image, a face, or is it not a face, is the problem. Verification is about, or authentication, is about comparing an input pattern with one specified stored pattern. So the person who claims to be person A, is that face person A or not? So you only have to compare the input pattern with this one person's data. And this is the problem at passport control in airports and so on. And a lot of systems work very well on this kind of problem. What's usually called face recognition is the slightly different problem of comparing one input pattern with n stored patterns and saying whose face is it. So is it one of the faces in the database, or is it a face that is not in the database? Obviously, this is a much more difficult problem in general. The opportunities for error are considerably larger. And the application context is quite different in each case. Failure to understand the differences leads to all these bad things, unrealistic expectations, wasted money, reduced security. The particular example, good example of this was after the 2001 terrorist attacks in the United States. Airports all over the US introduced face recognition systems. Anything's fine, just install something, doesn't matter what. And they had used a library of faces of suspected or known terrorists, supposedly, that they got from the FBI, and the system scanned everybody going through the airport, and the alarm went off, whoop, 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 if it spotted one of these faces or thought it did. And the problem with this is that although a system like that can work very well comparing an input pattern with one particular pattern, saying, is this the same person? In this face recognition context, because you have so many people coming through the airport, matching against so many people in the database, you get loads of false positives. And so the alarm is going off all the time, and what people do, what the security people at the airport do, is they switch the system off because it's too much of a pain, hence wasted money. And when the system is working, reduced security, ironically. Okay, so just to draw some pictures, face detection, we have our input can be a face or not a face. Output is, yes, this is a face, no, it's not a face. So the good outcomes are true positive and true negative when there isn't a face, and the system says there isn't a face. Errors are false positives when there's no face in the input, but the machine thinks there is a face, and false negatives when you miss a face that is in the input. Quite often in recall and information retrieval in general, we use precision and recall, which are these two fractions here. So precision is about the cases that the machine flags up, how many of them are correct. And it's an index of how many false positives there are. If there are no false positives, precision is going to be 1. And recall is about how many you miss. So it's if there are no false negatives, then recall would be 1. There's usually a balance between these two determined by some kind of threshold in the machine. Okay. Face verification, where the input can be person A or not person A, or somebody else. Output can be A or not A. So true accept is where the system says, yep, that's person A's face, and it is. True reject is where the system says that's not person A, and it isn't. And then there are two types of errors. There's a false reject and false accept. False accept is when some other person is judged to be person A, and false reject is when person A is not recognized as person A, although it actually is person A. And as you might imagine, this one is the most important. False accept rate is the most important for security, because you don't want to be letting the wrong person into your building or onto your plane or whatever. Okay, here's a couple of graphs. These kind of statistics are quite often used. A threshold in the face detector can be varied, and as you increase the threshold so that the similarity that the machine calculates has to be higher in order to judge somebody as present, the false reject rate goes up, and the false accept rate falls, false reject rate goes up. And the point at which these two cross is called the equal error rate, and that's often used to describe how good or bad a verification system is. If you take logs of the two scales, you get something like this. And another alternative way of representing this is if you plot false reject rate up the side and false accept on the horizontal axis, you get a thing called the receiver operating characteristic, ROC curve. This terminology comes from old radio receiver terminology. And the point at which, here's x equals y up here, and the point at which this ROC curve crosses it is, again, this equal error rate, same as here. Okay. In the case of recognition, where you have one input face and n faces in the database, the possibilities for what kind of mistakes you can make increase. So again, you have the possibility of getting it right, that's these light blue squares, getting it wrong by falsely accepting somebody else or nothing, or rejecting the same as in the verification situation. There's also the possibility now that person A will be, sorry, this column here, person A will be recognized as somebody else who is in the database but isn't person A, and so on. And there are a number of situations like that. This is false identification, where you've got somebody else recognized as somebody else, but it's a different somebody else. And you can approximate these statistics in terms of the same false acceptance rate for single person verification systems. Okay, just wanted to say that before we move on to the third part of the course, which is machine learning, which is a much bigger field in recent years, and is probably the most active field in computer vision in general at the moment, or in much of technology actually. So machine learning falls generally into these two categories, supervised and unsupervised. Supervised learning is sometimes called learning with a teacher, where you have labeled training data. So you're given a set of sample data, and for each sample you have a label saying this is a correct example of class A or class B or whatever. And this is used for training things like the k-nearest neighbor classifier that we looked at yesterday, training parametric classifiers, estimating the parameters of models for each class, and so on. Simple example of supervised learning is linear discriminant analysis that we looked at yesterday. A less simple example is the support vector machine that we'll look at a bit later. Unsupervised learning, or learning without a teacher, is learning from unlabeled training data. So this includes clustering, finding clusters of points in unlabeled data, estimating the number of classes, which may not, in situations where it's not known, and which class a particular sample belongs to, or an input belongs to. Again, estimating parameters of class models. A simple example of unsupervised learning is principal component analysis that we looked at yesterday. A less simple example is expectation maximization, or EM algorithm, which we'll look at today. So, first, this is an unsupervised learning. The simplest kind of unsupervised learning is clustering, for which we often use things called mixture models. Clustering is about trying to find structure in unlabeled data. So it's unsupervised, although you may know or be able to guess how many clusters there are initially. And it's natural to model distributions like this in terms of a mixture with one component per class or cluster. Now, just looking at this, you can instantly say, it looks like there are two clusters there. This is very easy for humans to do, but much less easy for machines to do, especially when there are more clusters than this and they're less well separated. So you could model this, you might think you could model this as a two-component mixture. That would seem obvious. One of the best known clustering algorithms is a thing called the k-means clustering algorithm. So you're given n data points, xn, and a fixed number of classes, big K, which is less than the number of data points that you're given. And your problem is to find the set of class prototypes. This is the mean, the center of each class, and an assignment of each data point in your training data to exactly one of the classes. So use this thing here, set this to 1 if your nth data belongs to the kth class, or 0 otherwise. And if you add up all these things for all these for a single point, for the nth point, it comes to 1, meaning that every point has to be in exactly one class, can't be in 0 classes, can't be in multiple classes. And the problem is to set these class memberships so that you minimize this error measure, this distortion measure. And okay, so what this is the squared distance between each point, each data point, and the class mean that it's of the class that you've assigned that data point to. So we're trying to minimize this. The solution is to randomly initialize, or not randomly if you have the luxury of more information, but in principle randomly initialize each of these class centers, and then we repeat these, what I've called an E step and an M step, because this is very similar or analogous to the EM algorithm that we'll be looking at later. In the E step, you minimize the error here with respect to the class assignments, which data is assigned to which class, without moving the centers of the classes. And then the M step is to, again, minimize the error here by moving the class centers around without changing the assignment of each point. That's one cycle. Go back to here and keep going until the thing converges. So that's a fairly simple clustering algorithm. I'll show you some pictures of it working in a moment. So we're trying to minimize this. The E step, the expectation step, means that the easiest way to do it is you assign each cluster simply to the nearest class center. That's the most trivial way of doing it. And the M step involves then recomputing the class centers using the revised class memberships there. And you can show that you can minimize the derivative of the error with respect to each of the class centers. You can set that to 0 to minimize the error if you set the class means, the class centers, like this. This is just the average, the centroid of all the data that have been assigned to the kth class. So here's some pictures of that. So this is a 2-class problem. Big K is 2. We start off with these class centers randomly chosen, deliberately badly chosen for this example. So there's a blue class center there, and here's a red class center down here. First E step is to assign each of the data points in our training data here to the nearest class center. So all these red points are assigned to this red class center. It was red class because they're nearer to that than they are to this blue class center. And all these blue dots up here are assigned to the blue class. Then the first M step involves moving the class centers to the average position of the red dots and the average position of the blue dots. So now the blue cross for the class center has moved to here, and the red class center has moved to there, which is the centroid of these red dots down here. Repeat that again by now reassigning all of the data to the red class or the blue class, depending which one is nearer. Repeat the M step, repeat the E step, repeat the M step, repeat the E step, repeat the M step. And after a few iterations, nothing changes, and we are finished. This is what the error that we're minimizing, that this J thing, this is what that looks like. You can see that after about 2 or 3 iterations, it's pretty much finished. Okay, so that's the simplest clustering, k-means clustering. You can measure data probability densities of mixtures of k Gaussian classes. When you do that, you get a thing called a Gaussian mixture model. So you can model each of those classes as a Gaussian with a Gaussian density. Probably, so the maximum probability is at the center and it falls off as you get further away. So this is a normal distribution. I don't know if everyone's familiar with normal distributions, but we often use this N notation here. So this thing is a normal distribution of these data X with mean mu K and covariance matrix sigma K. So this is the mean and the shape of the kth class. And we create this mixture density as a weighted sum of these individual class densities with the weights pi k there for each class. Okay, these are mixture coefficients, they're called, and they add up to 1. And you can interpret them as prior probabilities of each class, the likelihood, the prior probability that any given data will come from a particular class. Then you can calculate these posterior probabilities. This is the probability that a datum X came from the class omega K given X. It's called probability, it's read as probability of omega K given X. And you can calculate that from the inverse, this probability here, which comes from up here, and the prior there. This is Bayes' theorem again, which we mentioned yesterday. And if you expand it, it looks like that. So here's an example. Here's the red line here is a mixture of these three Gaussian densities in blue. The same data that we were just looking at can be modeled as one single class like that, which is not a very good fit, or it can be modeled as two classes like this, each with its own Gaussian density, which is much better. So some examples of Gaussian mixture models might look like this in 2 dimensions. This is a contour plot. Okay, that's these are quite commonly used as Gaussian mixture models are quite commonly used for real data where you have hopefully a known number of classes and they're likely to each be Gaussian for physical reasons, depending on the problem. Okay. These are usually treated using or estimated using the expectation maximization algorithm. We introduced some latent variables. Now, this used to be 1 or 0 back when we looked at the k-means clustering. These were 1 if the nth point belonged to the kth class and 0 otherwise. But now we make these continuous variables that control which class might have been, I'm sorry, they're not continuous. This version, these gamma are the continuous versions. So this is the same as in the class mean, the k-means clustering algorithm. And these are continuous variables which are interpreted as the probability that this label will be 1 given the particular datum xn. Okay, and you can calculate that to be this thing here. So we estimate the class means mu k and the covariance is sigma k, plus these mixture coefficients, saying how much of each of these class densities is included, using this expectation maximization algorithm. So EM is actually more general than this, and it doesn't have to only be used for Gaussian mixture models, but that's the most common thing that it's used for. Okay, similar to the k-means clustering that we just looked at, here's an E step and an M step, which are repeated until we converge. The error measure now has been replaced by a goodness measure, the log likelihood, and instead of minimizing it, we're going to maximize this. So this is the likelihood of the data, all the data. This big X is the set of all the data. It's the likelihood of all the data being as it is, given the mixture coefficients, the vector of class means, and the set of all the covariance matrices for each class. So again, we start with random initializations. We randomly initialize the mixture coefficients, class means, and the class covariances. And then the E step is to reevaluate the these so-called responsibilities, these continuous coefficients here, which are between 0 and 1, based on the current means and class covariances. And then the M step, again, updates the mean and the class covariances without changing the responsibilities. And we alternate between these two. Go back to the E step, repeat, and keep going. Okay, so the parameter updates look like this. This is the new class mean for the kth class, and it's calculated as this weighted average of the data where the weights are the class memberships assigned to this nth data. Class covariances are updated like this. This is the vector from the nth data to the mean of the kth class that's just been updated up here. And again, this sum is weighted by these analog values here, these gamma values. Mixture coefficients are updated as an average over, for each data here, these are averaged over all the data there. Okay. In pictures, which are a bit easier to understand, it looks like this. So we start off now with a symmetric Gaussian, unless we have a good reason not to. So these are circularly symmetric Gaussian. They look like a kind of a round pyramid, if you will. And we just plot them as a contour, effectively. So the expectation step, the first expectation step, assigns each data a color which is more red if it's nearer to the mean of the red class, and it gets gradually more blue as you get closer to the mean of the blue class. And the blueness or redness is given by that those variables gamma that we looked at, responsibilities, so-called. Okay, so having given each point a redness or a blueness, then we, at the first M step, we re-estimate the mean and the covariance, the shape of each of the class distributions. So given the blueness and the distribution of the points and how blue they are, we compute this as being the first update of the blue covariance and this as the update of the red covariance. Then keep doing the same thing over and over again until this takes about 20, after about 20 iterations, we get something like this with this particular data, which is, it takes a bit more, usually more iterations and quite a bit more computation to converge than the straight k-means clustering. Okay, here's an example with real data. This is, Old Faithful is a geyser, a hot water fountain in Yellowstone Park in America. And when the water shoots out of this geyser, there are long bursts of water and there are short bursts of water. Nobody really knows why, I think, but so here's a long burst of water, and then the delay until the next burst is longer if the bigger you have, the longer your previous burst. And it turns out that the data fall roughly into these two classes. So you can see with the initialization has both classes up here somewhere at random, and over the space of a few iterations, the classes converge something like this. Okay. So that's what EM, this is actually from the Wikipedia has an EM algorithm page, and this is from that. Okay, so the EM algorithm requires more computation than a simple k-means clustering and more iterations, but you get better results for classes with different or non-spherical or asymmetric elongated distributions. Sometimes you can set the initial parameters for EM using k-means as a pre-processing clustering so that the EM stage then converges more quickly. They can both get stuck, k-means and EM can both get stuck in local optima, so minima of the error for k-means, maxima of the log likelihood for EM, and neither of these algorithms is guaranteed to find the global best solution, unfortunately. So it does depend where you initialize the distributions from. to ensure that you don't get stuck in a local optima, good initialization is the key. They can also suffer from singularity, that's a numerical instability, if one of the data points lies exactly at one of the class means, for example. A more general framework for EM involves lots of latent variables and so on, but we won't go there. Okay, that was EM. Support vector machines are another kind of classifier, which were probably the biggest thing in pattern recognition until deep learning came along more recently. Support vector machines were invented by this Russian guy, Vladimir Vapnik, and the soft margin support vector machine was in 1995, so it's that kind of age, it's 20 to 30 years. And support vector machines are applied to a lot of supervised learning problems where you've got labeled data. And it solves a number of problems with the nearest neighbor classifiers, such as overfitting, excessive computation, and where you need nonlinear decision boundaries. Support vector machines are good for that kind of problem. There's a lot of software available. There's a thing called libsvm, which is open source, freely available. MATLAB uses SVM. The OpenCV is in what used to be Intel's open source computer vision system, and that is also based on libsvm, and this is kept up to date and maintained properly. So what does a support vector machine do? Well, it aims to maximize what's called the margin. If we have classes that are linearly separable like this, so linearly separable means these can be separated with a straight line, or in more dimensions it would be a hyperplane, not a straight line. But linearly separable means that there's this margin down here where you can put a decision boundary. So all three of these decision boundaries will accurately classify the data into blue crosses or green pluses, but they have different generalization performance, and the generalization is best if you put the decision boundary here where the margin, which is this m distance between these two lines, is maximum, for reasons that you can see visually here. Okay. So the objective of designing one of these things is to find where to put the boundary. You can assume that the classifier outputs a -1 or 1 for the two classes. So Z is the label that we're going to give each datum. And this hyperplane can be expressed, assuming the data for the space is X. We can express this hyperplane as an inner product of a weight vector W and X, plus some bias term. Now, in this case, the bias term W0 there just shifts this plane in this direction. Okay, so we can set the length of the W term such that this is true, such that this line is given by this thing equals 1, and this thing is given by this thing equals -1, in which case the decision boundary down the middle is this linear function of x here equals 0. Okay. And if you do that, then the width of the margin is given by 2 over the size of the length of the W vector. Okay. You can show that minimizing that the margin is equivalent to minimizing this thing, subject to these family of constraints. So for all of the data points, you want this thing to be true. What this says is that each point must be on or beyond this line or this line, meaning there's no points in the margin space there. So it turns out this is a relatively simple quadratic minimization problem, has a unique global solution, and importantly, although this must be true for all the points, you only need to worry and solve the equations for the points that are actually on the line. So for this thing equals 1, not the greater than 1. And those particular data, those xi for which this is true, are called the support vectors. And those are the points on the margin boundaries, like this one and this one and this one. So you can see visually from this example that having extra green pluses down here or extra blue crosses up here isn't going to affect where the best decision boundary is. It's only going to be affected by the points that are at the edges of the margin. Okay. So for details of this, we won't go into all the details, but you can see either of these textbooks if you're keen to get into it. All very well if the data are linearly separable, if you can separate them with a straight line or a hyperplane, but what do you do if they're not linearly separable? There are two things you can do. One of them is to introduce so-called slack variables that allow some of the data to be wrongly classified. And this is a thing called a soft margin SVM. Another thing you can do is to map your data space into a higher dimensional space where the data are more likely to be separable by a linear boundary. And that's a thing called Cover's theorem, says that you can do this. So for each of the data, you map it to some function of the data in a higher dimensional space. That can involve a lot of computation, but you can avoid some of that computation by using a thing called the kernel trick, which allows you to replace inner products of high-dimensional functions like this with a simple two-dimensional function like this. Or you can do both of these. Okay. So I'm not going to go into huge amounts of detail about the support vector machines. You usually don't have to go through the mathematical design of a support vector machine yourself. Given a load of data, you can, where was it? There it is. All you need to do is go to the libsvm homepage, download the software, and you're done. So, but if you really want to get into the details, then you're welcome. Okay, so the illustration of mapping into a high-dimensional space looks like this. So here's a space in which the data are not linearly separable, but they are separable by this boundary here. And the points on the margin of this curvy margin are support vectors like that one there and this one here. Mapping that into a high-dimensional space gives you points that are separable by linear margins here. Okay. The choice of kernels, I said you could do a thing called a kernel trick. There are a number of different kernel functions like this that you can use, and which one is used tends to depend on the data and what the distributions look like. Quite commonly used function is the radial basis function, which is essentially a kind of 2D Gaussian, or multidimensional Gaussian. So here's an example from the Chris Bishop's book, Pattern Recognition and Machine Learning, where we've got a blue class centered around there somewhere, and a red class. Well, I don't know if that's one mode. It may not be a unimodal distribution. Red data over here, and the support vectors, in this case, using a Gaussian kernel function, are these guys with the green circles around them here. Here's the decision boundary. Here's some more support vectors in the blue class. Okay, and you can't see it here, but the blue class kind of wraps around here. So the red support vectors include these, and then this contour kind of goes around here. So these are support vectors up here, and further up here is blue again. Okay. So this is a typical kind of result from a support vector machine using a radial basis function kernel. Okay. The soft margin support vector machine, we said that this is a solution that aims to allow a certain number of errors. So here's the decision boundary up here, and the support vectors are on this margin or margin boundary here for the blue class, and this margin boundary for the red class. And points beyond the margins are mainly blue, but there's a red one there, and mainly red, but there are some blue ones over here. I think this is actually a 3, looks like a 3 class, not sure. Anyway, and points within the margin, there are a number of points within the margin boundary here, some of which are classified wrong. Okay, soft margin again, if you wanted to build your own soft margin support vector machine, the easiest way is to go and use one that's in the software libraries like libsvm. Okay, neural networks. Neural networks are now the basis of deep learning, which is recently people have been calling it AI, artificial intelligence, although that's a much bigger field. But neural networks are in their having their third big period of activity right now. The first one was probably in the 60s, maybe, and they had a period of activity in the kind of late 80s and early 90s where everyone thought that neural networks would be able to solve every problem, and then it turned out that they couldn't, at least not then. But now they're really the best recognition solution for a lot of situations, and I'll talk about why later. But so what is a neural network? It's a network of units like this, which have a load of inputs. Here's an input vector with components from x1 to xd up here, so it's a d-dimensional space. There's also a bias term here, which is set to 1, and it has its own weight, W0 there. So this thing here it's called the activation of this unit, and it's the inner product of the weight vector, these weights here, times and the input vector x, plus this bias here. Okay. And the important thing about these units, or one of the important things, is this part, the nonlinearity here. So this is a nonlinear function f. Back in the day, originally, people used step functions. So something that's 0 down here suddenly jumps up to 1 up here. That's a step function. And you can use step nonlinearities, but there are some advantages if this function is continuous and differentiable. And we'll see what those advantages are in a minute. So this is loosely a simple, very simple model of a nerve cell like you get in the brain, which tends to have a lot of input synapses joined to the outputs of other nerve cells or neurons, and they are of varying strength, and the weights can change as the network learns, and that's what happens with artificial neural networks as well. Okay, this is called a perceptron. This is a word dating back to, I guess, the late 50s, early 60s, I think the perceptron model came from. The output, because of this nonlinearity, the output is this thing. So it's the nonlinearity F applied to the net activation, which is this thing in the brackets, and the net activation is inner product of weight vector and input vector. Okay. What can you do with a simple perceptron? Well, a single layer perceptron, meaning a single unit, a single perceptron unit, can implement a linear decision boundary in the input space. So here's an input space with vectors x. Here's a weight vector w. The net activation is this thing, and then applying a nonlinearity to it gives you the output y. For example, here, if y is less than 0 in this shaded area and greater than 0 in this half of the plane, the bias w0 here offsets the decision boundary from the origin of the space. If w0 is 0, then this boundary goes through the origin. Okay. So what can a single layer perceptron do? Well, like this, it can solve linearly separable problems, such as an AND function or an OR function. So here's an AND function. Both of his input number 1, or component number 1 of the vector x here, must be 1, and component number 2 here must be 1. They both need to be 1 for the output to be 1. Similarly, for an OR function, the only way to get a 0 output is for both of the inputs to be 0. If either of the inputs is 1, the output will be 1. So these can both be implemented as a linear decision boundaries. Exclusive OR problem, where you need exactly one of the inputs to be 1 to give you an output of 1, cannot be implemented with a simple linear decision boundary. It requires 2 layers. Okay. Which brings us to the 3-layer perceptron. So here's an input layer with some inputs here. Here's an input layer, here's an output layer, and here's what's called a hidden layer. All the layers, if there were more layers, all the layers between the input and the output layers are called hidden layers. You can show that a 3-layer perceptron like this can implement however complex you want your decision boundaries in the input space to be. And you can show that it can do this by having the hidden layer here implement AND functions, and the output layer here implement OR functions. So the input layer computes simple linear decision boundaries which chop the space in half. This layer then computes ANDs of the various regions computed by this layer, and this final output layer here computes unions of these regions bounded by hyperplanes. So if you have enough units in each of these layers, you can show that this thing can chop up the space as finely and in whatever way you desire, which is a theoretical result, but it is not a useful result. Okay, so, but it was one of the reasons why people thought Great, neural networks can do anything until they tried to do everything. So perceptron learning uses a thing called the Woodrow-Hoff, in the case of a single unit, or delta rule. It's often known as the delta rule for reasons that we'll see in a moment. So the basis of this learning rule is if a training vector x gets misclassified, then we change the weight vector of our unit. If the desired output is t and the actual output is y, so that the error delta is t minus y, then the weight update, this is the change in the weight vector w, is something, some constant alpha, times delta, the error from here, times the input vector. Something times the error times the input, and that's the delta rule. So here's a case where we have two classes A and B, and they're classified correctly by this choice of the weight vector W. Great. Then we've got an X here. This is a new input vector, comes along in our training data. It's from class A, but the system classifies it wrongly as B. And the way we fix the system, the way we update the system, is to add a little bit of the vector x here, which is this, to the weight vector, which rotates the weight vector from here round to here. And so the decision boundary moves from this solid line here to this dotted line here and correctly classifies x. Great, so in this case it solves the error and reduces the error delta back down to 0. With a multi-layer perceptron, if the non-linearities in each unit are differentiable, so they're continuous, they're not step functions, you can propagate the error in the output layer back through the network and gradually update all the weights in the network to reduce the error at the output. So here's the error in the output. The output vector is y and the desired correct output vector is t, let's say. These are the outputs of all the units in the output layer stacked up into one big vector. A thing called the sensitivity of the ith unit is defined as delta I, which is the negative of the derivative of this thing, the gradient of the squared error in the output with respect to the activation, that's this thing, of the ith unit. At this point, I haven't included the bias term W0, we'll just include that in the weight vector Wi here. So for the ith unit, Wi is the weight vector, Ai is the activation, which is the inner product of the weight vector with the input signal, the input vector to that unit. And then for an output unit, for a unit in the output layer, the sensitivity delta K here looks like this. This is the error in the output of that particular unit. That's the activation of the unit. And this F dashed here is the slope, the gradient of the nonlinearity at the particular value of the activation. So if I just go back to here, as the activation here goes up and down, you can see the slope, the gradient of the nonlinearity is maximum there, drops there, and drops there. Okay. And a thing called the generalized delta rule then gives the weight update for this unit as this thing. It looks like the delta rule that we saw on the last slide, but it's that you update the weight vector of the kth unit as by adding something times delta again times the input vector to that unit, which from this turns out to be this thing. Okay. X can be is actually the input vector to all units in the same layer. We consider them to be the same vector. Okay. So, so that's the units in the output layer. What do you do about the units in previous hidden layers? And the answer is you can propagate the errors back. I'm just going to go on to the next slide and then come back to this one. Here's the output layer. Here's the kth unit in the output layer. And here's the jth unit in the previous layer. And it turns out that when you update the weights for this unit, J, that's these weights within this ellipse here, you can calculate the weight update, which will reduce the error at the output from the errors at these output cells and the weights of these links here. Okay. I won't go through this in any great detail, but this is the update for the weights of this unit, the jth unit, and it's defined in terms of this is the slope of the activation at this unit, and this is a weighted sum where the weights are, these are the weights coming out of that unit, these three orange lines here. Weighted sum using those weights of the delta is the error at each of the output units, K, times the input vector X, which is the input to the jth unit. Okay, so for the output layer, this, for a previous layer, we have this in terms of where the update, weight update, is defined in terms of the errors at the output being back propagated. It's called back propagation because you back propagate the errors from the output back through the network to determine the weight updates. So this is what I just said about the next slide. This is the update rule, and you can show via the chain rule that it reduces to this thing. This is where the term error back propagation comes from, because these updates to the weights depend on the weights from the output of each unit to the units in the following layer, so we need to back propagate those. Generalized delta rule gives the weight update as this thing, where X is the input vector in general to all units in the same layer. And when people say neural network, what they usually mean these days is a multi-layer perceptron trained with backpropagation algorithm. Okay. And this brings us to deep learning. Deep learning is essentially learning with very deep neural networks with lots of layers and usually trained with backpropagation. And these are now heavily used for image recognition, speech recognition, data mining, sometimes labeled data, sometimes unlabeled data. This is an extremely active research area right now, probably the most active area of research in engineering. People like Google, Facebook, Microsoft Research are throwing huge amounts of money and people at this problem. The networks that are usually used are called convolutional neural networks, because going right back, what slide are we on here? We're on 109. Going right back to the start here, you may remember from yesterday that we had some filters, linear filter, this thing scanning across the image, a bunch of weights here, and an input vector here. and the weights were scanned across the whole image. And that's a convolution of the filter with the input image. Going back to where we just were. There. A convolutional neural network has weights repeated across multiple units in a layer. So this looks rather like a linear filter where the mask is scanned across the input. So there's shift invariance. This is called weight sharing. There's shift invariance so that an object can be detected, for example, at any position in an image. They have multiple trainable convolutional hidden layers. Recently, 100 or so is a quite regular occurrence. There are other operations done, such as normalizing the signal so it doesn't get too big or too small, taking local averages or maxima, and so on. But the main learning functions are done by updating the weights in the convolutional layers. Okay, training is usually done by some kind of stochastic gradient descent solver. The thing about deep learning networks is that they need a very large volume of training data. That's probably the biggest problem with them, is that you need a lot of training data to get them to converge. They usually tend to use GPUs. The graphics board in most computers, a lot of graphics cards now have multiple GPU chips on the video card, and these can be used. You can segment the problem and give some of the problem to each of lots of GPUs, which is the most efficient way of doing it usually. And you can protect to some extent against overfitting by using a technique called dropout, where only some of the units get updated at each iteration, which stops the network overfitting too much to particular training samples. Okay, so here's going back to 2012, one of the first deep learning networks was a thing called AlexNet, after this guy Krzyzewski, his name is Alex. And it had 7 trainable layers, which is not very deep relative to today. It took about a week to train by stochastic gradient descent on 2 NVIDIA GPUs. Input was an image, 224 by 224 pixel image, times 3 for RGB, and had about 7 layers. What tends to happen is layers tend to get smaller in terms of spatial extent, but deeper in terms of the number of different convolutions, the number of different filters applied as we go in. And then the final couple of layers are often fully connected or dense in this case. Okay. So this kind of network is used for image recognition, classifying objects in the input image into several categories. So the output at the end might be a 1 for the class of object that's being recognized in the input and 0 for all other classes. That's a typical kind of configuration. A couple of years later, Google came out with GoogleNet and built so-called inception modules. This had 22 trainable layers and 5 max pooling layers. In this picture here, the blue parts are the trainable convolution layers. The red bits do max pooling or average pooling, so the output of a unit is a local average or local maximum of the inputs. And the green bits are normalization or concatenation, which is joining two input vectors together. There were some additional side branches, which are these temp 1, temp 2, as well as the output here. These were used during training to force the input representation up to that point to be efficient, sensible. One problem with deep networks is that it's very difficult to know what is being represented at the inner hidden layers, and you can sometimes get quite inefficient, weird representations developing. So using this output and then using this output and then using the final output was a way to make this thing converge in a more sensible way and quicker. Okay. This also took about a week to train on pretty big GPUs. So this was 2014. Okay, so that was quite a well-known network. The year after that, Microsoft Research came out with residual learning. This was a network with 152 layers. And the idea of this is that instead of learning a mapping h of x, what each layer did was to learn the difference or residual between that mapping and an identity mapping. The reason for that was that a lot of layers, when you're training a deep neural network, a lot of layers compute something that's quite close to an identity mapping. It's only slightly different, particularly during the early stages of training. So rather than start from a zero or some random weight vector, the idea was that if you start with the identity mapping here and then just learn the difference between the correct mapping and the identity, the thing will, it's effectively a better initialization. So initializes the training from identity rather than from zero. This reduces the error, assuming that the desired mapping isn't too far from identity mapping. So this was 2016. These residual learning networks are still used quite heavily. Okay. Another advance has been so-called densely connected networks. Previously, in the previous examples you've seen here, the input to one layer came entirely from the previous layer, and its output went only to the next layer. But within each block here, you have connections that jump over several layers, and this allows more rich representations to be trained. So this DenseNet thing was published in January last year. Again, these tend to use 100 layers or so, containing several of these dense blocks, like this, in which all the layers are connected to each other. There are no backward connections. All of these connections are forward, but they sometimes jump over the layers in between. On this test data set, which is one of the publicly available data sets, the error achieved by this network was about half the error achieved by the previous ResNet, Microsoft's ResNet. And the computation and training are faster and simpler, although the network structure looks more complicated. Okay. So, recent history of object detection and recognition in deep learning networks looks like this. There was a competition called the ImageNet Large-Scale Visual Recognition Challenge, and that ran from 2012 to 2017. And back in the first time, which was 2012, the first time that a deep learning network was entered into this competition was there were 6 entries and only one of them was a convolutional neural network. But it won the competition. This is a 1,000 object classification task, and it's a top 5 error rate. So you're allowed to have, if the correct answer is within the top 5 estimated by your network, then that's given to be a correct answer. So this machine from Toronto University in Canada got a 16% error, which was considerably better than the best other system, and it was the only convolutional deep neural network out of 6 entries. The year following, error was down to 11, nearly 12%, and now 17 of the 24 entries were convolutional neural networks. The following year, Google's Inception network that we just looked at won with about 7% error, and at this point, there was only one entry that wasn't a deep learning network. So really, this whole thing happened within the space of 2 years. Microsoft's residual learning came along and chopped it in half again. And then 2016, Ensemble learning network from China got down to less than 3%. TRIMPS here is a government research organization in China. In 2017, SE, which stands for something, explosion net. Again, this is Chinese and British collaboration, got it down to just over 2%. Finally, DenseNet, I seem to have missed out the figure actually, but the DenseNet came along in January 2018. Okay, the last time this competition was run was 2017 because they figured the networks are just getting so good that we need a more difficult data set in order to make the competition interesting. So one of those data sets used for face recognition now, which is slightly different from object classification, was a thing called the Labeled Faces in the Wild data set. So this is a kind of data set where you don't have everyone looking like a passport photo and looking straight at the camera, because those are relatively easy. So in the wild means these are just randomly harvested photographs off the internet or whatever. So this is about 13,000 images of about 6,000 people. So about 2K of those have multiple images. So Facebook's AI group, which is one of the bigger ones in this area, got about 97% in 2014. National University of Singapore and Baidu, which is the big Chinese search engine, got about 99.7, as did FaceNet and Google in 2015. Again, this network, this data set, is now really, it's too small and it's relatively too easy to test for large-scale recognition. So people needed to have bigger data sets. Facebook won't make their face data public for obvious reasons. So a lot of public data sets were built and have been used. One of them is this thing called the IJBA data set. NIST is the US government National Institute of Standards and Technology. So they have a data set with 500 people, and for each person there are multiple images and videos, and they're generally much more difficult to match. And your system sits here and produces similarity scores for each pair of inputs. There are pose, illumination, lighting variations that make this set much more difficult than the labeled faces in the wild, and the couple of results over the past few years have gradually got better to the point where if a top 10 answer is okay, this is now over 99%. If you have to get the actual top position, it's over 96%. So that's pretty good. NIST, the US government runs vendor tests for commercial face recognition systems, and NEC has won it. NEC from Japan has won it for the last 2 years. The last report came out a few weeks ago, and the 2018 test has about 0.5% error rate on 12 million registered faces. So deep learning convolutional neural networks are now better than humans, at least under controlled conditions. Humans are still slightly better than neural networks under this kind of difficult condition like this, although we are not as good at recognition as we think we are. If you actually measure how good people aren't quite as good as they like to think they are. Okay. How are we doing for time? About 10 minutes. Okay, so other data sets that are around at the moment, there's a thing called the Common Objects in Context data set, which has quite a lot of images of quite a lot of objects from 80 categories, and there's so-called stuff categories, which are not particular shapes of object, but stuff like water, sky, foliage, etc. And there are a load of people in there as well, with some of them have facial key points annotated. This is another couple of data sets with object categories. Here are some of the examples for the airplane category. You can see that some of them are quite difficult in terms of variations of lighting and background and angle and so on. Okay, so this is an example of deep learning on the COCO, Common Objects in Context data set, where the objective is to find, for example, this fork, segment it so you identify not only what's in the image but where it is, draw a bounding box around it. So we've got fork, we've got this wine glass, we've got people, we've got this girl here, and so on. So this is the kind of task that you need to solve if you're going to find objects in cluttered images, or find people in cluttered images. And this example comes from, it's in 2015. Okay, so this is a fairly recent typical kind of example. So why is performance now so good? Why did it get so good over those, really mainly over those 2 years, 2012 to 2014? The answer is that you can learn more complex models than with any other kind of classifier. You can use more training data. In fact, you have to use more training data. And now more training data is available because there's a lot of images and video out there on the internet. Large-scale distributed learning is now possible because we've got faster networks and GPUs, and you can use, a GPU is kind of a network by itself, but you can network machines together and do a serious distributed learning with kind of data warehouses. There are more resources available. People like IBM and NVIDIA will give you free hardware or free cloud computing services since the ImageNet 2015 competition. You've been able to run your stuff on IBM and NVIDIA kit without paying for it. The dropout training algorithm has prevented overfitting, which was a problem in earlier neural network learning, any kind of learning. And there's all this open source free software available, including these software frameworks. The main ones right now are Google's TensorFlow system is the biggest of these networks. They've just released version 2.0 of TensorFlow. And in languages like this, you can specify numbers of layers, the non-linearity, the activation function of each layer, where you have pooling and maximum layers, what the error function should be in each layer, etc., etc. So you can specify all the parameters without having to program the whole network yourself. You can specify it quite easily. Keras is a high-level API which sits on top of TensorFlow. It effectively calls TensorFlow commands. It was a standalone application, standalone API for TensorFlow, but it's now, with the new TensorFlow 2.0, Keras is now integrated into TensorFlow as this module tf.keras. So you can just get hold of TensorFlow and Keras together these days. Previously, Keras used to use various types of back-end to do the computation, but now it only will be using, from now on, it will only be using TensorFlow. It previously used to be able to use Theano. CNTK is Microsoft's cognitive toolkit, and so on. But these are a bit older now. They've been more or less superseded by TensorFlow. PyTorch is a Python API. Python tends to be the most commonly used programming language for this kind of system. PyTorch is based on the earlier Torch, which was developed by Facebook's people. PyTorch is kind of an alternative to Keras that's a little bit more complicated to program, but you can do a bit more with it without having to get into too much detail. Okay. So all this is free. You don't have to pay for any of this. You can download all of this if you have a machine with a GPU in it, or even if you don't, you can use some of these on just machines with just CPUs. Main current development areas are image and video recognition, of course, faces, objects, actions, maps, terrain, road signs, video and archive indexing, automatic editing of video, automatic colorization of old monochrome video is an interesting application, self-driving vehicles for which you need pedestrian detection, traffic detection, and inter-vehicle communications, automation of basically everything, manufacturing, object handling, gripping, navigation around factories, process control, speech recognition and interpretation, speech synthesis, user interfaces, automatic translation, speaker recognition. And finally, games and strategy development. Games might seem like a funny example, but actually some games are rather useful at, because the rules tend to be very simple, but the strategies can be quite complicated, these can be quite useful in developing new networks. And Google and DeepMind, Google bought this company DeepMind a few years ago. A couple of years ago, they made this system that plays the game of Go, and they've just produced another system that plays the internet game StarCraft. This is the Go system. So 40-day training period, and this system, previously a lot of expert systems and neural network systems were trained by using human examples, past games played by humans. How do human champions play the game? Try to learn the same principles. But in this case, they ignored the way that humans had previously played the game, and they made the network play against itself and learn how to beat itself, learn how to win. And that made the thing develop some rather counterintuitive strategies, so not obvious to humans. So starting from 0, I'm not sure exactly what the index is here, what the variable up here is, but within a few days they had surpassed probably, I think this is one of the human champions from a couple of years ago. Where is it? It's AlphaGo Lee. This is a network that beat this guy called Lee, and after a few more training days, they had the system capable of beating, I think, whoever was the biggest master at the time. So, and after 40 days, the thing was essentially unbeatable. Okay. This is from DeepMind's blog. This is last week. They were playing this StarCraft 2 game, which is an multiplayer internet game. And they used a type of learning called reinforcement learning, where you effectively reward good results to update the network. And this system trained with reinforcement learning achieved very, very good performance on this complex game task. Now, I don't know anything about StarCraft 2, but I think this is, from the coverage this has got in the media, it seems like quite a big deal. And they used multiple agents, again, instead of just one. In the AlphaGo version, they use one alpha machine playing against another version of itself. In this case, they use multiple agents all playing against each other while all learning. So multi-agent reinforcement learning. So this is, right now, as of last week, this is the state of the art, pretty much. They had a publication, this is abstract of a publication in Nature, from 30th of October, so just over a week ago. And this is from their blog again. First AI to reach the top league of a widely popular sport without any restrictions. Okay, and the idea was that it would have to play against people and so they put the thing live, actually playing on the net against itself and against other people. And can play in one-on-one matches against, in these versions of the game. Training's fully automated and starts only with these agents trained by supervised learning. They unleashed it on the official game server, and you can go and look at all the replays here if you like. Okay, and that is it. If anyone has any questions, there you go, 6:01.